But I have seen that, I think they call it you saw it up there. Yeah, it looks like a big tree. No, I saw it somewhere.
Okay, we're going to start back in 5 more minutes. Dr. Lee's just finishing up, and then we'll be going.
And you saw you know what I think? When I got to see the shower, I thought it was nice.
It's a company that sets
September is going to be the warmest, right?
Yes.
I just want to make exactly about the today's 27th, last July 27th.
Where were you before?
So much cooler. 20 degrees cooler.
Do you have an HDMI port? No, it was,
Okay. All right, I wasn't sure.
Yeah, it's getting worse, right? No, darn.
Oh, yeah, well, I don't know. It's not following the same orbit.
It's
Oh, it's here. So it's not on.
Yep. But then, stop sharing.
So then if I share,
Advance.
Run by
Advance. Portion of screen. Hit this box, and now you open up the presenter mode, and you can make that box the size of it.
but isn't is it showing up now that I have two desktops? Right? Like
If you want to just share the desktop.
Well, and then this desktop is that.
Okay.
So I think that's just sharing,
Oh, I have the.
So yeah, so that seems like it needs to
We're getting closer and closer.
so then and then
Yeah, sometimes it's like, I know I've
beyond me. Like,
Hey, we're gonna get started back again. Can you guys hear me okay?
Oh, yeah.
Hey. So how the star formation process informs whether stars roam together or alone. Our host star, the sun, is often described as an average star. However, it appears to roam the Milky Way Galaxy alone, without another stellar companion. Studies have estimated that as many as 85% of all stars are part of a multiple star system, and this fraction is a critical component in models ranging from estimating local exoplanet habitability to interpreting recent James Webb Space Telescope observations of some of the first stars in the universe. Whether stars persist together or alone is determined within the natural clouds that collapse from hundreds to thousands of stars together. Most of these stellar groups eventually dissociate, releasing the newborn stars to roam the galaxy as collections of small numbered multiples. The mechanisms that group stars into these multiples have yet to be fully understood. So Dr. Lee this evening is going to talk and summarize our understanding of stellar multiplicity and how this may help address why our sun appears to be roaming the Milky Way Galaxy alone. Dr. Lee is a computational astrophysicist specializing in star formation, multiplicity within stellar systems, and the pedagogy of introductory astronomy courses. He earned his PhD in astrophysics from UC Berkeley and holds a master's degree in applied mathematics from Cambridge University. Dr. Lee's research utilizes national supercomputing centers to simulate the complex physics involved in the star formation process to determine how light-year-sized clouds of gas transform into the clusters of stars we see within the Milky Way Galaxy. What this means is you guys gotta pay attention. He has received numerous awards for his teaching and research, including an early career award from St. Mary's College. Outside of academics, he enjoys running, entertaining his cat Geo, and playing video games. He is particularly excited to teach his upcoming course, Choice, Can Video Games Teach Empathy, during St. Mary's month-long term in January of 2025. So everybody, please welcome Dr. Lee to the club. They got too close, they don't like.
It's all good. Can everyone hear me? Yes. All right, excellent. Thank you everyone for having me today, or tonight rather. It's a privilege actually to be back. It's funny how, things get lodged in your memory, and the moment that you come back to a place that you haven't been to in almost a decade, it immediately comes back to you. As soon as I pulled into this parking lot, I'm like, there's where the speaker parks, and then I go around the corner, and there's, a tray for food. Nothing has changed. It's good. So just to remind you, we were together in the past, so a little bit about me. I started UC Berkeley as a graduate student in astronomy in about 2008, and then I was doing my thing, and then it was in 2015 where I gave a talk to you guys on what was my PhD project at the time, of trying to figure out what's going on with those first stars. And there's a clip of the title slide that I had when I gave that talk. Once we parted ways, I kind of wrapped up UC Berkeley, said peace, and drove all the way, loaded my entire life and my cat into my car, and then drove all the way from the West Coast to the East Coast, where I started a postdoc at UMass Amherst. And again, a little feedback. Hold this back a little. All right. That postdoc was short-lived in that essentially the month I got there, the faculty member I was working with said, hey, I got a job at UT Austin, do you want to come with me? So we soon relocated to UT Austin, where I continued my postdoc for another couple of years, at which point then I was very excited to have gotten then a position at St. Mary's. So my net displacement from grad school to my job was about 10 miles, even though I looped around the entire United States. St. Mary's has been very weird. I came literally the semester before COVID hit. So my first year of being a professor was very atypical, and then of course we all know the years after that were nothing but, nothing like, normal. But it's been good. So as was mentioned, 2023, I was very humbled to receive an early career award. This year I was awarded early promotion to associate professor, which I'm hoping makes tenure in the bag, when I go for it this year. But of course, most importantly, this timeline shows that we've come full circle and I'm back here today, to talk with you guys. And again, yes, everyone please, fingers crossed, 2025, 10. St. Mary's, we're a little oasis kind of tucked away in the mountains of Moraga. If you've never been to campus, I really would encourage you to stop by campus one day. It is very, very pretty. I feel like a monk just walking around, and there are actually brothers, members of the LaSallian, branch of the Catholic Church that do live on campus. So you are really with, kind of, they call them monks. I kind of feel that way. But we also have a lot of really cool astronomy equipment, and one of my goals when I got back to the Bay Area was actually I was talking to my, friend Jeff Silverman, who we were grad students together at UC Berkeley, and we were both kind of the lead public outreach people who really enjoy doing public outreach. So I had this big goal that as soon as I got back to the Bay Area, I'm going to use all that big network I've created and, kind of hook St. Mary's into all this cool stuff that you guys are doing and that other people are doing, and then COVID hit and then I went to hell. But let me just kind of, introduce ourselves if you're not aware of us, kind of what's going on over in Moraga. We have a lot of cool astronomy equipment and a lot of nice open space for things that I think could make for really fun public outreach events or something that could kind of engage the local Bay Area community. Particularly, we have the Geisberger Observatory, which has a 16-inch diameter Schmidt-Cassegrain that has been currently being revamped and kind of refurbished. You will soon learn I'm not an observer, right? So I don't actually use telescopes. So I've more or less been keeping this thing in maintenance mode. But Professor Kittner took her sabbatical to kind of, in a sense, go from becoming a particle physicist to an astrophysicist. So she's been kind of revamping the telescope and getting it working. You can see, some pictures of the Milky Way Galaxy. We're keeping an eye on that nova, seeing if it's going to blow any day. Are other people kind of keeping track of this? T Corona Borealis. Good, people are watching. Yeah, we're hoping to catch it and contribute to the kind of public data collection ourselves. But then what I really think is cool is that we also have a lot of equipment that goes towards our undergraduate curriculum. We have a big observing pad. So these are in the mountains right behind campus. About you walk a mile, kind of into the hills. You find the observatory in this nice kind of open area. Very nice and concrete laid down and benches all around. Where we have 40 high-end binoculars, 6 kind of 4-inch stellar views that have kind of permanent mounts on the ground. COVID sale prices. I snagged a 9¼ diameter Celestron, for students. So we have a lot of stuff, so do keep me in mind, or keep us in mind, right? If you need other partners, moving forward, it would be cool to find similar collaboration. And there's other cool things that we're trying to do as well. I'm doing an upper-level astronomy class this semester, and naturally, where you teach a class that you haven't taught in a while, or that you're trying to change something, the rule of thumb, of course, is change one thing, and then see how that goes. My approach is usually change everything, and let's just see what happens. So I'm trying to do too many things. So we're gonna try. Like I bought star analyzer, that's essentially a diffraction grating. You can connect to your DSLR or a simple telescope. We're going to try to do some astrophotography and some low-resolution spectra. And we also are going to collaborate with the Stanford Solar Center, where they have these little kits you can buy for about $200, where they send you all the things you need to build essentially a little radio telescope, where we will monitor solar activity. So it just looks at very long wavelengths, and if a thunderstorm is going on nearby, sometimes you get a blip, or if there's a solar flare going off, sometimes you see an energy reading, thing. So we're going to try to do that. We'll see. But for the science. So my plan of action today is to kind of give you a broad overview with a smattering of results. I'll give you some details, of course, as well. Just first to give you an overview of the kind of general star formation process and what are some kind of open-ended questions that people are still trying to figure out. And then from that, go to talk about some of our recent results that have come out regarding molecular clouds. So these are the natal birthing grounds, essentially the stellar nurseries that stars form in. This will use JWST. I was asked to make sure I incorporate JWST in some way. Then talk a little bit about my own work, which is more kind of in the numeric simulation end, on formation, evolution, and dissolution of stellar multiples, so things like binary stars. How can we better understand binary stars? And then thinking a little bit more globally in terms of stellar companions, of the formation, evolution, and dissolution of stellar clusters. Our sun does not appear to be part of a cluster, yet it seems that all stars originally formed in clusters. So, where'd they go? That's essentially the open-ended question. So, let's start with kind of an overview of star formation. This is really the big picture. So, stars. My favorite objects, of course. Here are some stars if you've never seen one before. If you just look at this picture for a while, you notice a couple things immediately, right? You notice that they come in various colors. And this is a picture of a star cluster, so we know that they're all roughly the same distance from us. So the brighter ones do appear to be intrinsically brighter, not just because they're closer. And they come in different colors. Most stars seem to be some variation of kind of orangish red, white, or blue. I'm curious if there's ever been like an anthropological study to say, why is red, white, and blue the most popular flag colors? I claim, my hypothesis is that we have just been intrinsically, it's been forced upon us by the cosmos. So we can tell that stars have various brightnesses, various colors, and we actually know how to actually measure these things, along with their radii, their distances, their temperatures, their mass, their composition. And the fact that we can do all of that is simply remarkable. It was only a few centuries ago that astronomers said, we will just simply never know what stars are made of, because they're just too far away. But yet we can determine composition, radius, mass, all the properties of stars without having to directly do this. And I talked about this yesterday in my upper level astronomy class. What does it mean to directly measure the temperature of the sun? To directly measure the temperature of the sun means I walk over to the sun and plunge a thermometer into it. That's not something you can do, but yet we can, infer these quantities and learn a lot about these stars along the way. And then here, zooming out a little bit more, here's Andromeda. It's just made up of stars. Over 100 billion stars. There's probably 2 to 400, the number keeps changing, billion stars in the Milky Way. And when we look at other galaxies, they seem very similar in that they're made up of billions upon billions, sometimes trillions, in some cases of stars. So stars seem to be everywhere. They are kind of a fundamental building block, of the universe. We also live around a star. All the energy that makes up the biology here on Earth started as starlight. That's beyond just Carl Sagan's "we're made of star stuff," right? But just the energy itself essentially started as starlight, and then, through photosynthesis, other kind of biological, processes, became things that maybe was my lunch. So it's worth understanding how stars work, where stars came from, what stars are doing, since they do play an important role in terms of the light that we see and the processes that govern us here on Earth. And we have to first make a fairly big assumption, but one that seems to be borne out, that we know of our sun. And our sun is pretty close. It makes it, it's a nice thing we can look at and study in great detail. But there's still so much about the sun we just don't understand. We have to make the assumption that all those other stars out there are things kind of like the sun, right? Maybe some are bigger and smaller and whatnot, but it's not that our sun is made of mostly hydrogen and helium, but that there's some weird exotic iron star out there, or something like that. You have to make these assumptions, in order for your models to have some sort of, have some feet. That's a big step forward. It was a very big step forward. It was actually in some ways the last step forward that Giordano Bruno took when he simply in 1600 just suggested that those things out there, those stars, were like the sun. And possibly around those stars, there are other planets. And maybe some of those planets are like Earth. Church wasn't really thrilled about that idea, and so they burned him at the stake. Makes Galileo's house arrest that happened 33 years later not seem so bad. But he's like this, it is really quite remarkable that from just not having to really leave Earth, we can figure out all these things about stars and then start to ask even more detailed questions. So how do you do this, right? We'll skip over the how do we calculate all these properties. Let's assume we figure that out and I can determine all these properties. But once you have properties, you look for trends, right? If you want, this is astrophysics, not astronomy. Which is like a joke, right? Those synonyms. Or rather, my joke is, if you meet someone on a plane and they're asking you what you study, if you want to keep the conversation going, say you study astronomy. If you want to seem impressive, say you study astrophysics, but then it might be a little off-putting to them. And if you want to end the conversation entirely, say you study physics. Now the idea here is that if we want to apply the laws of physics to these stars, right, the first thing to do is to look for trends. So if you were to take my introductory astronomy class at St. Mary's, it's very similar to the very popular one that Alex Filippenko teaches at UC Berkeley. In many ways, I consider him kind of a mentor of mine, because I got the opportunity to kind of be his kind of head TA, a couple semesters for that giant class, and really learned a lot about teaching. So I do give him credit for a lot of my teaching accolades. But something you would do is you kind of look, you look at trends and you find, are there different kinds of stars and categories and things that can kind of, you start to group things together. And, historically, there was Harvard professors that would come up with all these categories, and we call them A stars and B stars and C stars. And then it was actually Wilhelmina Fleming and Annie Cannon, who they were the computers at the time, right? The ones that were doing all the number crunching in the background. It was mostly Annie Cannon's work. She realized that if you took the categories and kind of rearranged them a little bit, and instead went O, B, A, F, G, K, M, and L and T were added later, that you had a sequence that went by degree, that went from high temperature to low temperature, versus the thing that they had before. Now, why we didn't rename the categories and kept the letters, well, the first lesson I do teach in introductory physics, I'm going to swear, so I apologize, is that inertia is a bitch. But what we have here is we have a trend that we were able to realize that there does seem to be a trend in terms of stellar temperature. And then we realized that when we looked at other properties, other trends emerge when we have that same order. So that this is one of the things you would be expected to kind of memorize, right? OBA, FGKM, LT, usually come up with silly little acronyms, to do it. Historical one, which is not aged well. OBA, fine girl or guy, kiss me, and then maybe lovingly, tenderly. Alex Filippenko had a really good one. Oh boy, Alex Filippenko gives killer midterms. And laughing tyrannically or something like that. I had one student give me one, so I offer an extra credit point for those who come up with really good ones. Though I'm realizing now that ChatGPT actually comes up with better ones than my students submit. So I might have to rethink this assignment. But one student gave me this one year. I had to fail her, unfortunately. Only boring astronomers find gratification knowing mnemonics like these. That is good. I will give her that. That is good. I don't think she came up with it, but whatever. So you look for trends, and then we realize that when we had all these stars, and we realized that this sequence of letters also said something about mass, and not in temperature, and luminosity. Luminosity is kind of how much light comes off the surface of the object, and the radii. And the fact that these trends existed then said that there was some fundamental underpinning, that physics could explain. And so then we set off to kind of figure this out in the 18th and 19th century, and started to figure out kind of the physical origins for these trends. And they also revealed other interesting things about stars. Stars, our kind of basic, operation is that deep down in their centers, they are fusing hydrogen into helium. Secondly, if you want to be, anal, it's hydrogen nuclei into a helium nuclei. That's what's going on. And a little bit of energy is released along the way, and that's what keeps the sun hot, or keeps the star hot, and then keeps it glowing nice and bright, and not kind of imploding on itself, which gravity wants to do. So, imagine something like the sun. We now know that the sun has been doing what it's been doing for about 4.5 billion years, and it's about middle age. It'll probably going to do that for another 4 or 5 billion years. And it's going to bloat to this thing called a red giant. And then it's going to essentially just kind of, I call it a cosmic burp. It essentially just kind of like lets go of its outer shells, and that's what's called a planetary nebula. Again, there's another case where, why didn't we just change the name? It has nothing to do with planets, but it is what it is. But then when you look at something like, say, Betelgeuse in the Orion constellation, it's going to go through a quite different evolution where it will actually explode, as a supernova. Our sun will not explode. It will burp. But the thing that you can then calculate and realize, which plays an important role for star formation, is when you think of a massive star, you take a star that's 40 times the mass of the sun. So you might think then it has roughly 40 times as much fuel to burn through. You have a bigger gas tank, you presumably can go farther, right? But it's a big old star, and when we look at the trends for luminosity, that as you go, when you just go kind of in mass, right, so if you go from something like the sun, which is about 1, to something like 40, right, that's a factor of 40. But then when you go in terms of luminosity, let's kind of think of how much energy it's using up. It goes from something that's around 1 to 500,000. It ramps up really fast. It burns fuel at an excessively faster rate. So, as a result, massive stars must live very short lives. They party hard and die young. They have more fuel to go through, but they burn it up ever faster. And so they only live a couple million years. The trapezium in Orion, right, in the Orion Nebula, are one such collection of kind of those top-level stars, where they will only live kind of a few to tens of millions of years. So that means if we see a big, massive star, we know it can't have been there for very long. They just don't live very long. So if you see big, massive stars, that must mean that star formation has occurred sometime in the recent past. Recent in astronomical standards, of course. So that's important because essentially we use massive stars as tracers, and we look for massive stars as a way to then find where stars are forming. And now we have lots of other ways to find it too, but that was kind of one important way, where we could then start to trace the evolution of these things, as when they go from kind of just like normal star to these kind of big bloated things that might eventually explode. But now we want to go backwards, right? We want to say what happened before the sun was the sun. What was going on during those stages of the star's life? Well, we can return to the Orion Nebula. again, since there are massive stars there, that's suggested that stars must have formed there recently. We now know that stars form in these giant molecular clouds. They are primarily molecular hydrogen with kind of helium and pinches of other things kind of thrown in. That's essentially the composition you get from the Big Bang, plus some recycling through stars. Where stars kind of take some of that stuff, churn it into heavier elements, burp them or explode them back out, and the cycle repeats itself. That, of course, is important because that's what creates the periodic table. But in these star-forming regions, we see that these primarily exist in these spiral arms of spiral galaxies. So you might be aware that there's roughly kind of two kinds of galaxies. There's spiral arm galaxies, like the Milky Way. We believe our Milky Way is one such thing. They're kind of flat pancakes, that are kind of, all kind of swirling in some direction. They usually have kind of, a few, spiral arms. I had this big misconception, even as a physics major, right, up until, almost grad school, that I kind of thought that, okay, there were the spiral arms and then there's nothing in between them. There's plenty of stuff in between the spiral arms. There's just a lot of extra stuff in the spiral arms. They're essentially big cosmic traffic jams, where stuff goes into the spiral arms, kind of gets stuck there for a little bit, and then eventually makes it out the other side. But since you have a lot of stuff, that then gives you an opportunity to maybe let gravity do its thing and let all that stuff implode on itself. And that's what we see happening in things like the Orion Nebula. We essentially can see by looking at the motions of gas, or the motions of objects that you can see within these clouds, that these clouds are undergoing some sort of global implosion. Essentially, you get enough stuff in a small enough space, gravity is going to do its thing. Right? Gravity does not discriminate. Lessons for us all. It will always try to pull everything together. So what happens in these clouds is essentially that you get a bunch of gas in one space. And you might ask, Dr. Lee, how did you create that cloud in the first place? You tell me. We don't know. It's actually kind of an open area of research. Kind of where do these molecular clouds come from? There's a couple different theories of how they kind of originate. But let's just take it for granted that they're there as we see them. They essentially, as they implode, they're essentially just big swirling vortexes that, as they're imploding, kind of break off and fragment into all these little chunks. And those little chunks, most of them at least, go on to then condense and form into little pockets of hot gas that eventually become bona fide stars. So, just to give you some rough feel for the numbers, these things are kind of tens to hundreds of light years in diameter, masses that can be kind of like hundreds to thousands of solar masses. And by solar mass, I mean the mass of the sun. So I mean that this cloud is about 100 times the mass of the sun to 1,000 times the mass of the sun. And these are some of the, I guess, densest things in the Milky Way, other than planets and small things like stars and us. The Milky Way is, when they say space is a vacuum, it's nonsense. Space is, it's pretty damn close to a vacuum, but it's nowhere. There's definitely some stuff in there. Kind of roughly 100 particles per kind of cubic centimeter. Which does anyone have a feel for the order of magnitude of, if I took a little cubic centimeter of air in this room, how many particles would be in that little cube? Quite a few. Right, good. Half credit. Yeah. It's about 10 to the 19, right? So one followed by 19 zeros. So a few. So much more tenuous out there, but nonetheless non-zero. And even within these regions, right, I told you that we can see evidence for these little individual things, right? We can zoom in on these little things called dense cores, and we see that these little pores either have motions that suggest that they're kind of, imploding on themselves, condensing down, or some of them, and JWST is going to do great with this, because essentially they're so thick. Let's see, like that one on the top. it's not that there's nothing where it's black in the center, that there's so much stuff there that it's blocking all the light. You know, like a foggy day in San Francisco. You know there are lights on over there in the city, but you can't see them. Infrared radiation has a much better, way of getting out. So sometimes, one way that we can tell that these things are imploding and becoming stars is when we look at the infrared wavelengths, we can see infrared sources in the center, right? That there's something heating up. And eventually, slowly but surely, it kind of comes out of its little cocoon, as a star. So that's kind of the general kind of setup for stars, right? These kind of big molecular clouds. But again, we have the question of kind of like, where did they come from? Then we have the question of kind of what happens as the cloud implodes on itself and becomes this collection of stars. So again, gravity ultimately wants to just bring stuff together. And for stars, you eventually get hot enough that you start nuclear fusion and you become a bona fide star. Now it has competition in a sense. Gravity would do its thing. Everything would turn into black holes if there was nothing stopping gravity. But thankfully, I'm not falling to the center of the Earth right now because the Earth is pushing back up on me. That's a pressure that's exerting on me. Just like air has a pressure, that's kind of weighing down on my shoulders. These things kind of tend to resist compression. These are calculations I'm required to memorize by law because I study these things, right? That you can kind of figure out kind of, what are the conditions for when gravity wins. And so when those conditions are met, these clouds, you can see over the span of about 10 million years or so, kind of the cloud goes from this big gaseous thing to kind of dense collection of just a bunch of young new stars. Some of them might be very big. This could be like the Orion Nebula, right? Some of them would be very big. Most of them are kind of like the sun, or smaller than the sun. The sun is kind of an average star in mass. This is what we call a stellar cluster. Essentially, the cloud has essentially imploded itself to become kind of hundreds to thousands of stars, and this is a stellar cluster. And all these stars initially start kind of roaming around with each other. Now, those stellar clusters, that's another question we can think about. Now, what I do is I think more of a fuller picture, or really, what people who study this we know we know the gravity part, but now we want to kind of build in all the other physics that we know is present, because if we can understand the relative importance of all these different kinds of physics, then we can get a better sense of kind of what determines things like, is this going to be a big star, or is it going to be a small star, things like that. And there's a whole variety of things we can look at. Turbulence, just the fact the gas is kind of churning around. Magnetic fields. Magnetic fields tend to resist compression. Magnetic fields don't like to be pushed close to one another. You experience this if you ever try to push two north sides together. They resist that sort of compression. And I think I have some pictures to show this as well, right? So it's kind of a case of magnetic fields, that we can map magnetic fields. It's actually a very challenging problem. So we can tell that these clouds also are magnetized. So there's magnetic fields at play. Once the stars form, they start kind of interacting with each other. So you might have a binary star. That's kind of a very simple example where they kind of hang out together. But sometimes you get kind of competition going on, where if you have a lot of stars in the same spot, then they start really tugging on each other, and that can sometimes kind of disrupt things. So sometimes you get kind of nice kind of binary stars like this. They're kind of interacting with some gas. You can see the gas kind of getting swirled around these two binary stars together. Sometimes they compete. Newborn stars, especially the small ones, are very much like newborn babies in that they eject matter at both ends. These low-mass stars, particularly the small ones, have a very large energy injection through stellar outflows. Essentially it's just material that gets kind of redirected and shot back out through some sort of complex interplay with magnetic fields. So these stellar outflows, of course, then is trying to push things away rather than bring things together. So you have these outflows that you have to contend with as well. And then that's for the small stars. Then on the big stars, which are really bright, remember they're partying hard and dying young. So they're emitting lots of radiation. Though that radiation can start to wreak havoc on your surroundings. So the radiation here, essentially what you have here is you have a bunch of stars kind of hanging out here as a cluster. But there's enough big stars that they're essentially creating this big bubble, where the light from the stars are heating up the gas so much that the gas is essentially becoming this big hot bubble, around the stars, rather than something that's kind of cold and collapsing. So then you got radiation, going on, and other things too, like cosmic rays and stuff like that. And all this starts to play a role in terms of how the stars kind of start interacting with each other and how they kind of remain as a cluster. Because all these different activities are also kind of maybe even pushing some of the stars away from each other. So then you can start to ask, where do these clusters go? When you work in all of this physics, if I just think of the number of stars out there, right? You look at the stars in the Milky Way Galaxy, the vast, vast majority of them are not part of a cluster. Yet it seems that all stars start in clusters, so most of those clusters have to go away somehow. Some of them persist. The Pleiades is one such example, right? It's about 1,000 stars that just gravitationally, they just comfortably hang out with one another and kind of roam together. Versus our sun does not seem to have a companion. We're not part of a binary, and we don't seem to be part of a cluster anymore. So where did those clusters go? So we have to think about that. So what this all entails, and I hope kind of shows, is that the star formation process is very, very complex. It's a complex interplay of physics, which is what makes it somewhat a great part of astronomy that simulations can do really well at. And this really has only become possible in like the last decade or so, where we've been able to actually take all of that physics and put it into big simulations and do things like take something that's kind of like a big ball of gas, like gravity and radiation and magnetic fields and all that stuff, and chemistry and all that stuff, do its thing, and figure out via simulation what you get at the end of the day. And then you can look and see, based on the relevant importance of different kinds of physics, kind of like, do you get what you see out there in space? Because if I do a simulation and I get something that no one has ever observed and no one believes to be true for a second, well, I guess that's cool. I guess that's a good science fiction project I just did, right? What I'm trying to do is I'm trying to represent nature, right? But nonetheless, I'm doing simulations, right? Simulations are simulations, but I want them to be representative of nature, predictive of nature. So then that's where the observers come in, right? It's an interplay between observers who can say, hey, here's what nature looks like. We are taking actual pictures of nature. Make sure your simulations incorporate this. Or it could be that sometimes you can make predictions and go, and then other people can go off and go look for those things and predict it. I was talking about the Arthur Eddington eclipse example yesterday in class, where Einstein made this prediction and Arthur Eddington went and observed it. Einstein was an overnight celebrity in those circles because of it. So all this is to show that there's a lot going on with the star formation process, but some of the big questions that still remain are kind of like, where do these clouds come from, within the galaxies? And then when we look at kind of the various properties of stars, like how many big stars versus how many small stars, how many binaries versus how many not binaries. Star formation seems to suggest that essentially all stars out there should be part of a binary at some point. There's a famous astronomer in the 80s that said all stars are part of binaries, but that doesn't seem to be true. I would update it to say all stars are part of binaries at some point, but then something happens we don't quite understand. But most stars out there are usually part of multiples. So there's lots of questions to tackle. Let me just give you a smattering of some of the results that we've come up with over the last couple of years, actually. So One is just kind of updating our understanding on molecular clouds. The way I might kind of paraphrase it is stellar nurseries or stellar arenas. So, I'm not tied to this project at all, but it had some nice JWST images and had some pretty interesting results to kind of show you the sort of things that we look for and do as observers, right? So I want to show you something that's not what I do, so then the other two statements are on stuff that I do. You kind of get the whole picture. So essentially, what this project is doing is it's looking across the entire electromagnetic spectrum and using ways that we now know of to trace star formation to try to better understand how the star formation process works at higher resolution. So we know that there's these big molecular clouds out there. We know that they're primarily in spiral arms. But we can start to ask, like, is there different parts of the spiral arms where different kinds of clouds form? Or what about the center of the galaxy versus the outskirts of the galaxy? What about in between the arms? Sometimes you get star formation in between the arms. What's going on there? So observers can use the entire electromagnetic spectrum, all the way from radio. So these are the ALMA, results from the ALMA telescopes down in Chile, who is essentially, we're mapping radiation that's emitted from carbon monoxide. Terrible molecule for humans, great molecule for astronomy. Carbon monoxide is a great tracer, right? Essentially, if we see carbon monoxide, that's a way for us to know that there's molecular hydrogen nearby. So molecular hydrogen turns out to be very hard to see for some kind of quantum physics reasons. Then you can go to, so that's essentially tracing cold gas, right? And you need lots of cold gas to do that to become a star. So that's going to probably trace where star formation could happen. Then you get to the visible range, of course you see, pictures like, galaxies that we've seen from Hubble. But then we look at different, very particular kinds of visible light. Clearly this very particular kind of red light, it's called H alpha. It's a kind of light that hydrogen emits. That light turns out is emitted very copiously nearby regions that are getting heated up by massive stars. So massive stars kind of make the regions very hot, and then as they cool down, they emit this gas. So this is kind of tracing where massive stars are. And then when you go to the ultraviolet, that also is a way, in a sense, tracing where very young stars are, because you see very bright things that are very big, they emit lots of X-rays, but we also know they don't live very long, so they better be up, they're probably very young. So what this collaboration has done over the last kind of 4 or 5 years or so, now kind of really coming into its own with JWST, and this is a project called FANGS. Physics at high resolution in nearby galaxies. You always need an acronym, where what's capitalized and what's not capitalized seems to be, a dealer's choice. So FANGS aims to understand the interplay between the small scales, the clouds, and star formation within a galactic structure and galaxy evolution by combining observations and theory. A lot of words. So what they are doing is they're looking across the electromagnetic spectrum using ALMA, JWST, Hubble, BLT, which is also a kind of optical telescope, to get very, very high resolution photos of nearby galaxies. And using those photos, start to ask the more detailed questions about kind of like where in the spiral arms is all of this happening? And can it happen outside of the spiral arms? And then they can start to ask questions like, how efficient is star formation? Right, when the cloud implodes, is it 100% going all into stars? Actually, it's much less than that. But is that different in different places? And so what they did is they kind of took these a handful of nearby galaxies, so you could get really high resolution images with these telescopes. And they broke them into different regions. So you can kind of see that they broke it into things like what's called the bulge, which is essentially the center of the galaxy, the disk, right, the pancake part. Some spiral arms have this bar that essentially it rotates like a solid bar, right? That kind of, doesn't spin kind of like a galaxy, but it kind of rotates like a solid bar. Some galaxies have them, some don't. Within the spiral arms, there's kind of this ring about halfway out, that's a resonance, and then some other things that are going on as well. And then they started to ask kind of the usual questions that we ask, but kind of, in these kind of new subcategories to try to figure out what's going on. I'll just kind of give you a quick kind of highlight of the results. Essentially, the first thing you might ask is, where is the star formation happening, right? We said spiral arms, is that actually true? And so they could calculate kind of like, essentially, how much gas there was, we just look at this column and this column. Essentially, how much gas there is to form stars, and then how much star formation we actually see happening. What we find, what they found, is that the centers of galaxies essentially have a mind of their own, and they're kind of churning out stars at a rate that's quite different than the rest, the other parts of the galaxy. There's a lot of material, and it's being very efficient at turning it into stars. Then within the spiral arms, that's kind of what comes in second place. The bar also as well. And then kind of in between the spiral arms and kind of outside of the galaxy. So this kind of matches what we would have expected, but it's nice to now be able to kind of put some numbers to these things. Because if we see something that's atypical compared to this data, then that suggests something fun is going on. One thing I brought up is this idea of efficiency, that stars, you have to have some stuff to turn into stars, but then think about all those things we talked about earlier, right? As the stuff is trying to become stars, right, there is kind of jets and magnetic fields and there's all this stuff going on that might hope to disrupt the process. If that happens, right, then it doesn't become a star, or it becomes a failed star, a brown dwarf. And in those cases, maybe, right, that means that the star formation efficiency is lower. It's not as efficient. Now, I was always taught, like, the spiral arms are where stars form. What they found, I thought, was actually quite interesting, is they don't worry too much about understanding, the violin plots. I do like violin plots, they're very thick. They're essentially telling you that just, did you ever learn in school, like, there was a box plot, or a box and whiskers plot? You had median, the quartiles, and then the mode, and then the max and the min. Is this just me? All right. Look up box plots. But essentially, this is doing the same sort of thing, where you're seeing kind of just the range of data, the medians in the center, but then you're seeing also kind of how the data is distributed as well. So there's more data here than there is not here. That's all it means. So what they did was the same sort of question, right? Kind of ask, how much stuff is there to form stars? How many stars are being formed? And then essentially, the ratio of the two tells you kind of the rate or the efficiency that material is being turned into stars. And what they found, what they did is they compared the spiral arms to the kind of in between the spiral arms, where I always thought there was more or less no star formation going on. There's not as much, but there is some going on. Turns out it's actually more efficient in between the spiral arms. The spiral arms have more stuff, but probably through feedback or kind of stellar competition, they're kind of getting in each other's way. And that material is not becoming as many stars as it could have compared to if it was somewhere else. That's something that was very new to me. That's interesting. Because now we're starting to learn kind of like different regions of space are creating different kind of overall end results for how many stars and what kinds of stars. And then that's going to help us explain kind of what we see out there. So that's kind of one cool thing I thought, that came out of this. Well, just the idea of binaries. Right. My subtitle is where I am pretentious enough to update a famous in my circles quote from a well-known astronomer. I kind of already did that earlier. So the idea with binaries is that you go outside tonight and look up into the sky. Most of those stars are stars like our sun, or kind of around our sun, and it's about roughly 50% of the stars, that are kind of like the sun, have some sort of binary companion. Our sun does not seem to have one, but For kind of sun-like stars, it's about 50%. Turns out when you go to more massive stars, that number increases essentially to 100%. The really massive stars always have another companion that they're kind of whipping around, doing their own thing. So why? Why is that? Especially because if those big stars don't live very long, then that means maybe that binary formed essentially, yeah, I'm sorry, zoom. I'm walking all over the place, I'm sweating up here. That, essentially, since those big stars don't live very long, that means that that binary probably formed when the stars formed. So it kind of formed as part of the process, versus two stars that kind of found each other in the night and then kind of, locked together. So the kind of formation of binaries, right, is an interesting question, especially because when we look at star-forming regions, like those big clouds, we find that there's even more binaries in those regions, right? So something's happening and going from the star-forming regions, where essentially more or less everything is in a binary at some point. That's my update to the quote. So there's a famous star formation astronomer, Larson, who he essentially said that all stars are parts of binaries. We now know that's not true, but essentially my kind of work that I did as a postdoc, essentially we updated the quote to say all stars are part of a binary at some point. Right? That binarity is really common, but sometimes it gets disrupted in some way. So we studied this, and this is really hard to do. There's a project one of my students is working on that we're not quite yet ready for me to talk about it, but essentially when people want to find binaries, you might think, if I see two stars that do this, well, I got a binary. But the typical time it takes for two stars to go around each other once, on average, you just pick a random pair of stars, is usually hundreds of years. I'd be fired immediately if I required a student to wait around, right, to get that data before I let them graduate. So what they do, and then it gets even worse in these star-forming regions where you have all this gas kind of making the picture, messy. Where they essentially see two dots, and they say they're close enough, they're a binary. It's a little bit more sophisticated than that, but there's that sort of idea. So one of my students and I were trying to see how machine learning approaches could be used, since we're now getting a lot of new data from JWST and Gaia in these regions, that maybe there's a new criteria we can come up with for labeling stars as binaries. We only get kind of a snapshot. That's the thrill and the headache of astronomy, right? That everything happens on timescales much longer than human lifespans. The rare exceptions are supernova and, gamma ray bursts. So we essentially only get a snapshot of the sky, and we have to figure everything out. So what I did as a postdoc, to study these sorts of things, was just like, how do binaries form in the first place, and then what happens to them as they evolve and become, stars in a cluster, and then maybe that cluster eventually goes away. Essentially, you do this through kind of big fluid dynamic simulations. You take these big boxes, these big numerical boxes, and first thing I do is I want to make the box look like a cloud. So I take a big digital spoon and I kind of stir them up to make them have representative characteristics of the sort of things that we see out there in space. It's not that I'm trying to exactly replicate the Orion Nebula. It's that I'm trying to do this in a statistical sense. And what we looked at is kind of what happens when you have a strong magnetic field, a medium magnetic field, and a weak magnetic field. So essentially we're testing what is the role of the magnetic field in this case. If one of these looks closer to what we see out there, that might suggest that, okay, the magnetic field might be playing an important role, assuming that it is actually that strong. And if none of this gets the right answer, then that probably means we're forgetting some physics, and I need to redo the simulations. So then what you do is you essentially then have these kind of regions, and each of these kind of represent just a part of the cloud, And I let kind of physics do its thing. And gravity starts to kind of pull these things together. You can see little dots start to pepper around. These are little digital stars that are forming in my simulations. And what happens is they notice that they all kind of start bunching together, right? Let me replay it. So the one on the left is a strong magnetic field, and then you're going to a weak magnetic field if you want to help, distinguish the difference between them. So as these kind of these filaments clump together, right, you start getting little things that appear, and a little cluster starts to form here. But then there's so many stars here that some of them even get whipped out. There we go. And then little clusters form there. And we then can look within these clusters and determine which of those stars are binaries, because in a simulation, I have a lot more data than the observers have. So I can figure out, through animations, that's kind of fun, where you have these stars kind of all whipping around one another. These are kind of 4 stars. You're looking at the same 4 stars, but kind of like through the side, through the top, and through the other side. So you're seeing them kind of whip around one another, but they do seem to be hanging out together, right? So this is not just a binary, but it's probably like a binary attached to a star. So you have this 3-star thing going on, and then that's all kind of paired to the 4th one that's kind of on the outskirts. So you have this hierarchy of multiplicity that's going on. And sometimes they switch companions, or it's kind of like a barn dance, right? They kind of switch partners. That actually was a big takeaway of this paper, is that we found that any 2 stars don't really seem to hang out together for very long. They kind of do this kind of, swing your partner, to someone else, sort of thing. So what we found is that essentially all stars do form with companions and hang out with companions at least for a while. Sometimes they get thrown away. Sometimes they kind of persist. And we kind of worked out kind of the time evolution of these things, and we were kind of able to kind of reproduce what we see, given that the magnetic field is playing an important role. So now we're kind of hoping that some observers will go kind of like try to do a better job studying these magnetic fields. So essentially, again, what I'm doing is I'm trying to simulate physics, and from those predictions, we can then try to see if they match nature or if they need some sort of, if it requires a reformulation of the model as a way to try to understand the relevant physics. This is very intricate and hard to kind of disentangle. And there was some work that we did with some Chinese astronomers where they took my simulation and then they did some calculations on it and turned it into something as if it were kind of out there in space and they had observed it with a telescope. They essentially, predicted how much radiation would be coming from all those stars and the gas, and they turned it into an astronomical image. And then they were able to match it actually to some of the things that they were observing in one of their observations. So we were able to kind of connect theory and observation in a really kind of nice way. All right, last but not least, which is my favorite one. It is brand new. So brand new that in trying to make this talk tonight, I had to rely on slides that I did not make. But that's okay, because I think the credit is well deserved, because it's my students that I'm pulling my slides from. These are 2 students that worked for me over the summer. We have a summer research program. It's a 10-week kind of program where they do work with a faculty member. I think it really is very unique for a school as small as St. Mary's that we can offer something like this. They looked at the big groups that formed at the end of the day. Right, this Orion Nebula has this cluster, and the Pleiades, right, that's a cluster. And we distinguish these clusters essentially with 3 different names. So once these clouds collapse and form into clusters of stars, you have OB associations, don't worry much about the name. So the Orion Nebula is one such example. These are big stellar clusters. Lots of stars, 1,000 or so plus stars, that have all kinds of stars, small stars, medium stars, big stars. And we don't see these last very long, but we have a good explanation for that. There's big stars in these things, and we know those big stars go kaboom, and so that bomb that goes off essentially destroys the cluster. And then all the other stars get kind of flung out into space. There's the intermediates, the open clusters, like the Pleiades, where it's kind of 100 to 1,000, kind of medium and low. There's no big stars, or there's very few big stars, so there's no bombs that are going to go off. And these we do see. The Pleiades is one such example. We see these stars kind of, if they all form together, and then we see that their ages are billions of years, then that suggests that they've been hanging out together for billions of years. Where it gets interesting is the low end. It's called the T associations. These are associations that are kind of at the small end of the spectrum. Very few stars, kind of usually like dozens to 100, of mostly small stars. So those stars, smaller or about the size of our sun. Now there's no bombs going off. But the interesting thing is that we don't see them live very long. We don't find any of these T associations that are older than, say, a few million years. Which would make sense if you had a bomb, a supernova go off. But where are these things going? We don't find any old ones. Our hypothesis is that these smaller clusters essentially have a few stars, but they essentially aren't very efficient. Essentially, there's a lot of leftover gas that they're kind of hanging out with. And that leftover gas is still kind of gravitationally holding on. We think if you were to let that gas go away, then essentially the stars would lose their grip on each other and move away from one another. And here's the idea. Remember, these small stars are babies that eject at both ends. So if you have this cluster, and what we think goes on is all these stars in this cluster are doing something like that. Baby's first photo. As these jets kind of shoot material back out into space, those kind of jets can push away the cloud, so that the cloud over time kind of fades away. And if the cloud is gone, then there might not be enough gravity to hold the stars together. And maybe the stars then gradually dissipate. So maybe T associations gradually destroy their home and leave. So what the Matthews did, the math squared, is they did n-body simulations. So they did simulations of, essentially, little point particles that are whizzing around one another. But then they had a little model inside the simulation to incorporate this cloud that they just let kind of gradually fade away. And they either let the cloud fade away really fast, really slow, and then they also looked at whether or not there was a lot of cloud or not a lot of cloud. So that's what these axes are. Essentially, this means the cloud goes away instantly to the cloud fades away very slowly or never. And then here, essentially, it means there's lots of gravity from, that should be gas. So this is gravity from gas, and there's lots of gas. Essentially, gravity is all from the gas, and here gravity is all from the stars. So you might think then, if you have lots of gas that goes away really fast, that might be something like what might, make the stars lose their grip. So to give you a sense, kind of like, this is kind of roughly, where we observe these associations based on kind of how old these things are and kind of how much gas versus stars there are. And then there's the open clusters that are up there. So what was really cool is what they were able to do is they essentially would take one of these things and they would first create these little clusters. So they would have little, about 200 or so stars that would be whizzing around. And they just give you a sense, right? The dots are the stars, and then that kind of like purplish pink thing is the cloud. To represent the cloud on the plot. And in the plots to come, or in the animations to come, you'll see that it might gradually fade away. So in the case on the left, there's lots of gas tugging on those stars, so they're whipping around. Versus here, there's not a lot of gas, so the stars aren't being whipped around so much. So you might think, if you're whipping, swinging something on a string, if you're whipping it really fast and then you let go, it goes flying. Versus if you're kind of just barely doing anything and let go, it just falls down. So here's what they found. Here's an open cluster test. So lots of stars. The stars can essentially hold on to one another And in this case, the you can see kind of the cloud fade away when the simulation repeats itself. So essentially we have the cloud kind of fade away, and the stars kind of just keep hanging out where they are. Essentially the stars hold on to one another. If you want to get really physicsy, essentially we can quantify this by looking at energies. Like kinetic energy wants to spread things out. Gravitation wants to kind of bring things together. Notice that gravity is above kinetic, so gravity wins, right? Gravity holds things together. That's all that means. Then we have this kind of T-association test. So something more like that. Let's start over. They're whizzing around, but the cloud, when it goes away, the stars lose their grip. The gas isn't able to hold on, or when the gas is gone, they can't hold on. And then we had this fun kind of intermediate case where it kind of bloated, where the star, like it threw away some of them, but not all of them. It was kind of in this intermediate region. We call them bloated clusters. But what we found with this kind of simple model, let's see, what is this plot? Is essentially, for the T-associations, we found they go away in the right time scale, right? They don't stay around very long. And the open clusters, even when the gas goes away, they hang around. So this is promising. Promising in that this is kind of on the right track. And so now we can kind of go and make, better models to build off this idea. But I thought this was exciting because it's suggesting we may have some mechanism to explain this quirk out there in the Milky Way. Why are there no young associations of stars? And this also suggests that why most of the stars aren't in clusters. Right? Those open clusters persist, but then the T associations eventually dissipate, and then the OB associations eventually explode. And all those stars then roam the Milky Way as loners, or maybe with their little companion. Let's see. So that's just some of my takeaways, right? That the star formation is complex and fun and interesting. And then JWST is going to do a heck of a lot and kind of informing kind of our understanding of these things. I gave one example. There's many more examples I could have given. And then what I think is kind of interesting is looking at this kind of stellar companionship. Either on the small end with binaries, because binaries, right, essentially, I should have said this at the beginning, they play an important role essentially across all of astrophysics. That nova is one such example of a binary. Right? That's the case of you had what used to be two stars. One became a white dwarf, and now the second one is going through its kind of stellar burst phase. But it's getting so big that that the white dwarf is starting to actually snag and start to steal some of that material away. And if you know anything about white dwarfs, you know that you can't make a white dwarf too big, else it explodes. That's what's called a type 1a supernova. I think it's actually interesting, I looked this up today, I didn't realize this. If you look at the mass of the white dwarf, it's about 1.36 times the mass of the sun. And essentially the theory says you can't go beyond 1.4. You don't need to add that much more mass before that white dwarf explodes. So one of these novas, who knows, maybe one day will actually be a supernova. And then this kind of cluster thing kind of goes at the same problem in the larger scales. So thank you for listening and for sticking with me through that. And I know we're a little bit over time, but I'm happy to either hang around and ask questions, or maybe we can take a few questions now.
Thank you, Dr. Lee, so much. That was great. I do think we have like 5 minutes maybe for a couple of questions, if anybody has them. I'm going to walk over with the mic for the
Great question. So the question was, what about those globular clusters? Aren't you forgetting one? You're right, I am. But they are a different beast. So globular clusters are another cluster of stars, but they have millions of stars, and they're all exceptionally old. They're essentially the oldest things in our galaxy. That is one of the ways that we date the galaxy. Essentially, because it's hard, to say like when was T equals 0 for the Milky Way, because it was probably this very chaotic thing going on when it formed. But essentially, we look for the oldest thing in the Milky Way and call that the age of the Milky Way. Just like how you can't be older than your mother. You know, the Milky Way had to form before things within the Milky Way then formed. So these globular clusters, we think, did not form through processes like what I was explaining, but through some other kind of like more larger cataclysmic collapse. That probably was, occurred kind of like as the galaxy was taking shape, and we think spiral galaxies kind of form through just a bunch of small galaxies kind of merging with each other. So that kind of chaos probably then kind of, squished, some regions to become these globular clusters, right? But yeah, they're a whole different beast. But very interesting as well.
So we know that the sun is not like a common star in the galaxy, so I was wondering if this type of studies can tell us something about the regions in the galaxy where sun-like stars form, so these preferential regions of the galaxy that form this type.
Yeah, so I think something that the molecular cloud study, the first kind of result project I showed, we'll be able to maybe say something a little bit more about is, because essentially when we look at different parts of the galaxy, and actually when we look at different galaxies, other than the Milky Way, essentially when you look at what kinds of stars are forming, it's always the same kind of distribution. What do I mean with that? Right, so I mean that essentially that, if you have a region that forms one massive star, 3 stars like the sun, and 10 brown dwarfs, then over here, if there's one massive star, there's going to probably be roughly 3 stars like the sun and 10 brown dwarfs. That's what's called the universal mass function. Though people have been starting to nitpick that, right, and trying to figure out kind of like when is it not universal, which might mean that you form kind of a different kind of distribution. So you're exactly right. This common mass is kind of taken as a global, like just taken globally. But now we can really start going into the details. But yeah, in terms of mass, the sun is the garden variety star.
Okay, one last question. Yeah, I do have one online from Nathaniel. He says he missed the first one. Was it about globular clusters? How do those fare? I assume that very old stars would be stable and likely to stay put.
Say it one more time, sorry, that started going off.
How do globular clusters fare? I assume that very old stars would be stable and likely to stay put. Question mark.
Yeah, that's yet another kind of reason, a good point, of why globular clusters are their own beast. Because, yeah, it's a bunch of really old stars. So again, it seems to be the lesson of today. Big stars party hard and die young. Right? If you have a bunch of stars that are all 10 billion years old, then you know none of them can be massive stars, because those stars only live a couple million years. So all those stars in the globular cluster are all very, very small stars, which, many of them have ages that, exceed the current age of the universe, right? I forget what the cutoff is, but there's essentially some range of masses where even if those stars formed at the Big Bang, which they didn't, the universe is simply not old enough yet, for those stars to have died. I guess debating on if you've been following this kind of Hubble constant issue, that we've been having, where maybe we got the age of the universe wrong all along. That's a different talk. Ask a cosmologist from Berkeley to talk about that. But yeah, so the globular clusters, and they're roaming not within the galaxy. They're roaming essentially in the outskirts, what we call the halo. So they're not hanging out in the pancake, but they're kind of roaming above and below the pancake. So they are very much isolated in that regard. So, good question.
All right, thanks everybody for coming. Thank you, Dr. Lee. That was a wonderful presentation. All right, we'll see you next month.
Yeah, and I can hang around if you have an extra question or two. Sure.
Molecular clouds, where
Yeah.
do they come from?
Thank you. So it comes up primarily because they're primarily made of molecular hydrogen.
Okay,
Um,
but where does that come from?
Great question.
So our current model is, because we have lots of evidence for just atomic hydrogen. It was the Big Bang created, all the hydrogen out there.
Oh, okay, so it's already all down then.
But that's not molecular hydrogen. Molecular hydrogen means I have to get those two protons to hang out close to one another and not repel, right? Which electricity wants them to do, but they have to kind of hang out, and they have to have a bond, which essentially is, you have to share electrons. So what we think happens is that when you look in these regions, there's, mostly, hydrogen and helium, but then there's also what we just call dust, and it is essentially what you think of when you think of dust. Fall over the podium. So there's these little kind of just like very like, just like carbon or silicate kind of, just like, structures that our current model that we think that kind of two protons kind of like land on one of these things, kind of roam around, find each other, smooch, and then essentially, just kind of jump off together. And they give all that, if they had too much energy, they would kind of jump off and go their own ways. But they essentially kind of, dump it in the, in the dust grain. That's a very common occurrence in astrophysics. Usually, if you have some energy that you want to get rid of, you have to find a third body to dump it into. Yeah.
Thank you very much.
Yeah.
Very interesting.
You're not saying hydrogen atoms can't get together unless there's already silicon to get them together? No.
Well, that essentially you can work out like kind of like the estimations of if you just have kind of protons, flying around in space, they essentially have too much energy to, or it would be too rare to reproduce how much molecular hydrogen we see, right? So that it cannot produce enough, fast enough, or at the right rate to kind of match nature.
I have a question about so what do we know about the environment where the sun was formed? Like what type of cluster?
Yeah, that was my first idea for this talk. Just like, what was that natal, cloud and cluster like?
Was it the association?
And like, I don't know if this is becoming popular or if I just haven't noticed this until now. But like new books and review articles I've been reading, essentially we'll have a little section called, called the sun's stellar cluster, where essentially people are looking at, so essentially and this is very, very hard to do. And I'm not an observer, so it's completely, magic to me. So essentially, you can imagine, if you had stars, that were part of a cluster, and then they all kind of decided to go see ya. Then maybe you could look around and see, and if you saw, okay, those stars are going that way, and these stars are going that way, and these stars are going that way. And I play the movie backwards.
I was having a question, can we figure out what sibling components of the
But then, if they start interacting with other things, right, then they get kind of jumbled up and mixed up, and then how do you know, what's the original and what's the jumbled, So, yeah, and so we don't seem to have I feel like I remember it in our radiation course, one of the professors sketched something about there's some bubble or something around the sun that they think might have been the original cloud or something, or a remnant of the
There's
cloud.
also research into solar twins. My
yes,
Iván Ramirez at JWST, where you can get really, really detailed observations which we have of the sun. You look for, all stars are basically hydrogen. Everybody gets it. The closer you look, the more detail you get, the more ratio of different elements and stuff. And so compositionally, if you look for other stars that are not too far away, that have really, really similar composition to the sun, you could say, oh, they all came from the same cloud of elements. So that is a field of astrophysics. I don't know how good that is. It was just my office mate in for a few years did that. So he's an expert on that stuff. But yeah, he wrote papers on solar twins. Other stars are as close to the sun as possible chemically. Maybe they were,
And there are some candidates.
He wrote papers that said solar twins, so presumably,
Really numbers were used.
Yeah. But
And it's a cool idea too. Of just thinking about, it's what is this? Because if you think about what does the sun's birthing ground look like? It probably look like what most other stars' birthing grounds look like. Because the sun seems to be very common, and the solar system doesn't seem to be I guess that's special, you know, maybe it's special in that like there's maybe not enough Neptunes, like I feel like.
I was wondering also like how, like you said that there is star at some point early on, it's also developed a multiple system with like everything like that.
Yeah, so there's
So
a lot of it.
exponential information as well.
I don't know enough to give you the answer, but I can tell you the number of papers I've seen talk about that has definitely increased.
Like if the sun had a component.
Right, because we have examples, right? Kepler 16 or whatever it was, you know, whatever the name is, right? But you know, the press called it, you know, a real life Tatooine because it was a star. It was two stars and then a planet going around the binary. Right? Yeah, and like people are thinking about, like I would have thought it would be very unstable, right? If you had kind of big tugs coming from two different directions, then you probably wouldn't get a nice circle. You'd probably get some like, you know, lopsided thing. And then the seasons would be kind of, you know, unpredictable, and you need kind of stability for evolution to do its thing. Yeah, that's why, you know, when I do intro astro, I always talk about like the moon. If we did not have the moon, like, because we have the you know, the tilt of the Earth as an axis. Because of the moon, right, it does this. Without the moon, it would do kind of this. Yeah. So over like thousands of years, right, the seasons would dramatically change, which is not great for evolution.
It's like a non-scientific question. Like I'm now a postdoc, like looking for jobs. I'm mainly in biology. So I was wondering also, there is a department. I never thought about like some medical scholars. I don't know if this is the department of biology.
They keep turning things on when people start saying something important. Say it again.
Yeah. Do you have guys like a department of biology?